So today we are going to dive deeper into various EM-based techniques, and you will be excited to know there are so many techniques other than what you know. So here are the uh, different techniques based on transmission electron microscopy. Of course, there are many based on scanning electron microscopy, but that will be taught in a separate lecture. So let us go one by one slowly so you can understand. And if at any point you have any questions, please do not hesitate to ask me. I know that most of you are from chemistry background, and it will be a nightmare for you to read these details. But believe me that past several generations of students have shown tremendous interest in this course, and they were very successful in this course. And I mean, successful means in not in taking good grades. I can't promise you that, but successful in terms of understanding it, taking part in interaction, asking right questions, and all kinds of interactive things. So I hope that this batch will be equally or more interactive as the students of previous batches were. So far, I'm not very happy with the interactions which I'm getting. Even attendance is quite poor. Yeah. So conventional imaging techniques, there are two. Most of the time, what you call it as a regular T image is actually the bright field image. This is the uh, if you see any TM image, um, where you see some particles, so you can uh, assume that it's most likely that it is bright field. And in bright field TEM, you see the particles as dark color in the light background, and the image or the contrast consists of three things: the thickness, crystallinity, and the atomic number, right? So higher the atomic number, heavier the atom is, so that is going to look darker. So because it will stop more electrons. Number two, bigger the particle, it will look darker because anyway it will stop more electrons. Less electrons will reach to the detector. Similarly, if it is crystalline, so what will happen that it will diffract off uh, certain electrons, certain percentage of electrons. In another direction, theta direction, right? As per the Bragg's law. So those are the three main reasons which decides the contrast of T images. Right? So the particles which are electrons which are coming straight, right, and will be diffracted off. Right? So in normal bright field, you collect the electrons which are coming straight. Right? Straight. Some of them are blocked. So some of them are diffracted by angle theta, right? Let me have a. So if you have, for example, and some of them are diffracted at an angle theta. I think somebody's mic is on, so can you please mute yourself? Yeah, thank you. So if you collect these electrons which are coming straight, anyway, some problem was there. So or diffracted electrons. So diffracted electrons, if you collect, so that will form diffracted dark field image, right? So similarly, you can do electron diffraction, selected area electron diffraction. So you select an area. That's this technique is called SAD. So there, these uh, 000 diffracted electrons, the straight electrons which are going straight, those are called 000 diffracted electrons. They form central diffraction spot, and the electrons, if you collect at a certain angle, so they will form different dots. So convergent beam electron diffraction. So here electron beam is converging at a single point, right? That is called convergent beam. Everything else remains the same. So normally in a routine TEM, the electrons are traveling a parallel path, right? They are traveling parallelly to each other in a routine TEM. But when you make a nano probe, so you can call it convergent beam, as the name suggests. And electron diffraction, if you take electron diffraction, what is the difference? Here the area selected is several hundreds of nanometer, but here you can get diffraction from a very small area. So, and you can scan or you can map actually. This contrast imaging, this is one of the most used techniques, which we call HRTEM. It is not the same as a stressed version of bright field or dark field. Many people think that if we keep on zooming high resolution TEM, you will get phase contrast imaging. Not at all. Very different technique. And this is basically interference based technique. So you see dark and bright dots, which represent actually rows of atoms. Okay, Z contrast imaging, we know that Z contrast, Z basically is your elemental uh, mapping. Energy dispersive X-ray spectroscopy. So when you uh, are interested in knowing which element from the periodic table is present in the matter, so what you do, when you bombard the electrons on to an atom, so some of the core electrons are kicked out from different atoms. So, uh, so the electron from the higher orbits, they occupy that empty space, and then an X-ray photon is emitted. If you capture that X-ray photon and analyze its energy using a spatial detector, semiconductor-based detector, so the energy of that electron is directly proportional to the atomic number of that element. And that was the finding of Mosley, who missed the Nobel Prize long back because he died in the World War. I think I told you the story about him. The next part is electron energy loss spectroscopy. So this has been discussed earlier, but I'll be discussing it later on as well. So these are the electrons which undergo some loss when they interact to the atom or lattice, actually, the periodic arrangement of atoms. When I say atom and when I say lattice, the interaction is very different, actually. When I say atom, I'm emphasizing on electron interaction, the interaction of the electron, which are part of which I'm bombarding onto the material which I'm investigating, and those bombarded electrons, high energy electrons, will interact with the electron which are part of the atoms which you're probing, as well as the nucleus, the positively charged nucleus through Coulombian interaction, right? So that is the electron atom interaction, right? But there are certain features which are part of uh, lattice, actually. When you arrange those atoms in a periodic lattice, so then there is a concept of what we call it phonon. Phonon is basically lattice vibration. So there are two types of lattice vibrations. Cations and anions can move in a different direction, right? Because of the electric field. When you apply electric field, so direction of the electric field will pull the positively charged ions in one direction and negatively charged ions in one direction. So that will create a wave in the lattice, right? Up, down. Or in certain case, what can happen that these atoms will move together like a Mexican wave, actually, no matter whether they are cations or anions. So then we can call it as acoustic waves. So those are the phonons, actually. So electron also induces phononic vibrations, actually, in the lattice. It's like you beat the fence with the stick, right? So it will make a noise, right? Like some jingling noise. So you can consider phonons uh, as if there is some jingling noise when you beat the fence with the stick. Another very interesting interaction is the creation of plasmons. Plasmons are actually the oscillation of electrons around the nucleus. I think somebody raised the hand, so you can ask the question. Unmute yourself and ask the question. Yeah, somebody has raised the hand, so I'm not sure. I'm not able to see that. Okay, so please ask question. Okay. You don't need to raise hand. You just ask a question because it takes a lot of time for me to check who has raised the hand. Believe me, if you are a presenter in Zoom, Zoom is much better. Teams and other applications are much worse in checking what you guys are doing. So I just have a presentation in front of my eyes. Okay, so few other techniques are Lorentz microscopy. This is very good technique. I'm sorry. This is very good technique for the people who are looking at some kind of magnetic systems. Actually, this is very good technique for magnetic particles. Right, I'm sorry, there is some. And another is electron holography. Electron holography is very good for ferroelectric systems and environmental control TM. We have already discussed. Cryo TM we have discussed. The cryo TM, actually, you know that it won Nobel Prize, and all this virus research, COVID research is happening using cryo TM. In situ TEM and environmental control TM is more or less the same. TM tomography is similar to the other tomography which you see. You can construct a three-dimensional image of any object, right? Okay, let us move to the next. Okay. So, so we would like to survey the most important technique of today, the modern technique. This is one of the most important technique, scanning transmission electron microscopy. So you can see that you are doing transmission electron microscopy in the scanning mode. So what is the difference? So difference is that, so suppose you have this sample where you have your atoms which you want to investigate. What you want to investigate in the this arrangement of atoms. So there are two things: what kind of atoms these are, and in what arrangement these atoms are placed in three-dimensional lattice, and also what is the shape and size of this cluster of atoms, right? That is the third question is a very trivial question, but first two questions are non-trivial, that what kind of what these atoms are, and what is the arrangement in which they are sitting. Those are the two questions which today's scientists, they are interested in. Any material which you study, any laboratory across the world, even on Mars, okay, Mars rover is looking for the same question. Please believe me. Mars rover, which landed recently, is looking for exactly the same question on Mars. It will be okay. So it does not have luxury for transmission electron microscope there, but it can safely do some uh, it can safely do some spectroscopy, and it is doing some spectroscopy like FTIR and U visible spectrometer, the same techniques, probably X-ray diffraction also there on Mars. So it looks for the mineralogy of the Mars surface, and it picks up the signal. It cannot bring back. I mean, it's a one-way ticket actually. Okay, if you are planning, if any of you are planning to go on Mars, and you have given some money to Elon Musk, and please make sure that you say goodbye, Tata, goodbye to all your friends and parents and everybody, because it's going to be one way unless you are taking them with you. Okay, and make sure that you take all your EM and everything there, so you can investigate these questions that whether what kind of elements are present dominant there, what kind of new interesting material formation is there. Okay, as of now we know that it is called red planet because there is plenty of iron. Somebody will answer me what is the reason that Mars does not have its own um, I mean Mars does not have a magnetosphere, so it has a lot of iron. Mars environment is very different than Earth's environment. It is not livable. What are the reasons? Somebody would like to tell me? Hmm?
Because it is cooler than the Earth's atmosphere.
Anisha,
It is
I cannot.
cooler, so it lost
Can you
its
repeat?
magnetic properties.
Sorry.
Because it is cooler than the Earth's atmosphere and it lost its magnetic properties because
When I
of the
say
changing temperature.
no, your question is slightly correct. Let me tell you. So when you say your temperature, even your temperature, like my temperature or your temperature, body temperature, there are two temperatures, right? One is skin temperature, and another is core temperature, core body temperature. So what matters more is the core temperature. The same thing is with the planets Earth and Mars. So what we are looking, not we are not talking about skin temperature, the crust temperature. Like here
Core
we
temperature.
measure the core temperature. So Earth core is still it has molten iron, which Mars does not have. Mars does not have molten iron because there is. We are lucky that there are some radioactive. You can thank physics actually for that, for your existence, Manisha. You exist because, or you can blame physics for your existence, uh, right? Which I always do. मैं क्यों पैदा हो गया or whatever. Some people become more philosophical, existential questions. You can always blame physics because there are some radioactive isotopes still there in the core of the earth, which are emitting a lot of energy, and that has kept the core very hot. So there is a molten iron, which is spinning and creates magnetic field, which does not exist on Mars, though it has a lot of iron, but it does not have molten iron actually, right? So that's why Mars temperature can be very hot or very cold. Okay, so it's extreme actually, and when it is very hot, so all the water actually just evaporates. So there's not much water, or people are trying to investigate. So scanning transmission electron microscopy is essentially when you are trying to investigate. You are in the scanning mode, right? So you are scanning this area. This is your electron beam, and then you bring the beam here, and you are scanning it here. In regular transmission electron microscopy, as I mentioned, that these are your atoms, and you are bombarding electrons which are falling straight, not in an angle. They are coming straight. Okay, so so you get the information from a specific selected area. Okay, you do not get the information from select your tiny area here under the, so the area under probe becomes smaller here actually. It's the advantage. So here you don't need to scan the beam. Okay, you don't need to do that. You can just magnify, demagnify, and select the another area. But here it is, you are like scanning the a beam, like you move the laser pointer on a presentation. When you're doing presentation, you move the laser pointer in different direction. So it's like that. So it combines the principles.
Hello, sir.
Yes.
Sir, then what is the basic difference between scanning transmission electron microscopy and only scanning electron microscopy?
Yeah. So good question. So that will be answered here. Yeah, it is answered actually here. The question. So this is the difference which the student was asking the question that let me first tell you what is SEM. In SEM, so this is the sample. Okay. Uh, okay. So more or less actually, I mean, it's answered here. Yeah. Okay. Let me see. No, this is STM only. No, I'm looking for the detector. That detector that makes the difference actually. I'm looking for the detector which it is there. Yeah, it is there. Oh, ACD. No. Let me see. Secondary. Okay, so the difference is that you have. Okay, let me go step by step. So your question is actually part of the slides. So it basically combines the principle of TEM as well as SEM. So TEM has a power of transmission. So you are looking at the electrons which are transmitted. In SEM, first you have to understand what is SEM. SEM, you are looking at not the transmitted electrons, but the electrons which are part of the sample, which are generated by. So basically, suppose this is your sample and you are bombarding electrons. What will happen that, so if you are looking if your observer is here, you're looking at transmitted electrons which are transmitted through the sample. This is called transmission electron microscopy. And SEM, you are looking at the electrons which are part of your sample. So they will be, so your detector will be somewhere here or somewhere here. There are two kinds of detectors. One is in-lens detector, another is Everett Thornton detector. Whatever, more popular is ET detector, Everett Thornton detector. So this is basically called secondary electrons detector. Secondary electron detector. Um, SED, not SED. SED. I think I saw it here. Yeah, this is the detector. See it here. Okay, so this is actually SEM built-in STM. So you can do STM in SEM also. So in SEM, you are scanning the beam, but you are not collecting the transmission electron, but you are looking at the secondary electron. Is it that, does it explain your question?
Yes, sir. Means in STEM, the detector will be below the sample, and we will scan
Yes.
the beam, but the detector will be below it.
Yes. But you can put other detectors also. I mean, you can put regular detector. For example, you want to look at the chemistry of the sample. You want to look at the type of. Okay, you want to collect X-rays. Different detectors you can put. Suppose you want to.
Okay,
So,
sir. Means can we collect same data, TEM data, or STEM data in a single machine?
Yes. Hold on. Very good question. Very good. It's. I'm actually showing it. So as like TEM, STM requires very thin sample. Okay. For example, NCL has got this quanta machine, quanta SEM. There you can put STM sample holder. I will show you the sample holder. Let me show you the sample holder. And let me go step by step. Otherwise, one of the principal advantage over TM is that it enables the spatial correlation of signals, including secondary electrons, scattered beam electrons, X-rays, and electron energy loss. So from the same area, you can collect many samples. So this is a beautiful picture. of cerium doped manganese oxide nanotube. Okay, this is a sample, cerium dope. So manganese oxide nanotube. So so this is first one. This is very rich, uh, uh, image with a lot of information. So this is a HADAF image. And you might be wondering what exactly is the HADAF image. HADAF is full form is H for high, A annular, a high angle annular dark field image. So here, this is basically jet contrast image. So the more white area, I think I explained, Manisha also asked this question about HADAF. It is similar to the backscattering. Basically, more heavier elements, atoms, will scatter more here. So if you see more white area, that means there are more number of atoms and more heavier atoms actually, because you will get, and it is in the STM mode. So that's why resolution is better. So you are scanning step by step here. It's not like regular TM image. So basically you can correlate. So you can, suppose you have one point here, another point here, another point, same point, you can correlate. So you can zoom this area, and zoom this area. You can match. यहाँ पे वो वाला atom कौन सा यहाँ पे क्या है. For example, you can correlate at the same position. You can capture the information actually. Here you can see, say, cerium doping. Here you can see manganese. Here you can see oxygen. Okay, though oxygen is not you can't be very confident, but these days aberration corrected instruments can show you some details about oxygen as well. And this is another beautiful picture which I have taken from the paper. Reference is always given in, you can see the reference as head footer. In the footer you can see. Okay, suppose you want to see details, you can refer to that beautiful paper which I picked up. So these are actually iron oxide nanoparticles, quite favorite, many people synthesize. So it is written as FeXOY because we do not know whether it is Fe3O4 or Fe2O3 alpha or gamma, whatever phase it is. And these particles of assembly of iron and oxygen atoms are coated with a surfactant, which is here, which is oleic acid. Okay, you can see that here. You can see. Okay, so so you can see that B. Let us start from the image B. B is elastic filtered HRTM image of a group of nanoparticles showing crystalline cubic structure. So in the inset, so here this is called selected area electron diffraction. So this is electron diffraction image. So similarly, what you do in X-ray diffraction, here you can index the these spots. So the center spot which I was telling is 000. You can see 220, 400. So you can, in fact, you can calculate the d values from this. And this is 001 is zone axis. I will explain it in the next round. What is zone axis? How do we index these dots? Okay, and what is the difference between X-ray diffraction and electron diffraction? That is perennial part of discussion in our course. So you can see that these particles have some spacing, right? They are not exactly touching each other. So this is because of the oleic acid, which is a carbon 16, 16 carbon chain molecule, long molecule. And similarly, you have one layer on the neighboring particle. So that's why there are two chains actually, one from this. So that is keeping these particles quite separated. And you can see here, at least you can see the rows of atoms actually. I mean, when I say atom, please be careful. I have already defined that you do not see atoms, but we, in layman language, we are telling that these are atoms. But I told you in the pure physics term, there is nothing called atom. It's just a collection of these particles. And what we see is basically the image of Coulombian interaction actually, right? Okay, potential distribution. Another thing which you will notice, whether suppose you call them as an atom, so white particles, white dots will be atoms or black dots will be atoms. So that question will be answered at the end of this course, because you need to learn hard way through a lot of interesting things before that, so that you can understand that concept. So this is corresponding Hardaf image A. You can see that as I explained earlier, that here the bright spots are the areas where more electrons are reaching. I mean, everywhere here actually you can see that the darker areas means no electron is reaching here, right? Brighter area means there are more electrons which are reaching. So that means those are particles actually. Okay. Any question here? So you should understand this image. If not, then it will be clear to you in the next. I mean, in future also. Don't worry about that. If you do not understand at this point, do not worry too much. Only I request that you look at the notes again and you listen to this video again, and because you have luxury now. Earlier, this luxury was not there. So so these are all taken from STEM. This is possible because of the power of STM. From the STM is actually a machine equipment where you can do all kinds of. So you can have EDAX detector, you can have backscatter detector, you can have SEM detector, which is basically your secondary electron detectors. So this is STM control. You have a camera here. Okay, yield spectrometers can be placed here. So you can see that here this is a narrow beam which scans actually. If you see all that, so you see this arrow, right? That means its beam is moving, and you can see that at one time you are looking at one atomic column. If you notice this, you are looking at one atomic column. Please note my words. It's very serious. It's not a joke. Actually, it's very serious thing. Whatever I'm telling you, that you can look at, you can image one atomic column. Actually, it's really I can we always joke, is it a rocket science? Yes, it is a rocket science. Actually, it's as serious as rocket science. Okay, so these detectors we'll discuss later on. Okay, so another example, I have put plenty of examples here. So this is intermetallic platinum manganese, I guess, yes, platinum manganese nanoparticle. So you can color code. So using STEM, you can see that you are able to color code atoms. So red atoms marked with red are platinum, and atoms marked with green are manganese atoms actually. And so this is, isn't it beautiful? I mean, it's very exciting that you can see atomic layers so clearly. I mean, so clearly you can see actually. uh, so this is, I think Manisha was asking, how do you know that this is platinum? So this is Hardaf image, and Hardaf, you know that it shows you jet contrast. So we can calibrate this, and we know. So you can see the scale. This 1 nanometer. किसी को मूवी देखनी हो तो बता देना आज. And you can see that this image was published. I found it at Cornell University website, and it was published by their Department of Chemistry and Chemical Biology, not by Department of Physics. And the people who were investigating this material, this alloy, platinum manganese, who are the people who were working on energy, actually, fuel cells, in a proton exchange fuel cell. So you can see that it has become interdisciplinary. You already see the Nobel Prize was given to the biologist. So it is extremely useful. So you can see that here we have 200 electrons which are coming. Then you have a condenser lens, and then you have condenser aperture. So through the lens arrangement, I will tell you how do you make the beam the way you want to. Suppose you want to make beam like this, or that's what you do. Even using this glass, as a kid we used to focus defocus sun rays, right? Our eyeglasses do the same thing, isn't it? So here the lenses are made of uh, magnetic field. So you can see that now we are able to reduce the probe size. This is amazing actually. It's not a joke. I mean, it's really marvelous. It's just marvelous actually. And here you see that this is CS value is 1 millimeter. Defocus is around 55 nanometer. I will explain what is defocus. See, in TEM, the difference between TEM or whatever STEM and your mobile phone camera imaging, or your regular SLR, is that you get the best image in optical imaging, geometric optical imaging, when you focus, right? When you focus on the object in the object plane, you get very good image. But did you notice that here you are getting the best image when you are not focused? You are defocused actually. What is the reason that you need to defocus? Electron microscopy. In electron microscopy, you get image, high quality image, when your defocus is proper. If you focus properly, you will not get an image, because the reason is right here, CS. So there is an aberration. So aberration is sort of counterbalanced to some extent by this defocus actually. To some extent, because there are other problems also. Now you can see the probe size is so small, 2 angstrom for high resolution, 1 nanometer, 10 angstrom for analysis, high resolution imaging actually. Okay, so this is the detector. You can see that this is an annular detector, right? Annular detector. The cross section is shown. So you can see that these are high angle diffracted. These are actually incoherent electrons, and they do not have crystallinity contrast. So that's a blessing. Earlier, these electrons, which are going away from the Bragg, away the diffraction angle is really much larger than the Bragg diffraction. They were considered useless, but people found that they have very good Z contrast. So now there is another detector. Concentric detectors are there. There is a Gartan dark field STM detector, and this is the third one. You can see the look at the detector. So, so let us go one by one. So this is the main detector. This one, beach wala jo hai. This is basically which you use for regular TM images. When I say regular TM image, something like this. I think I showed you earlier. It's not here, but it will be something like this, but not exactly this. Okay. So this is bright field image. You can take because bright field image you get using the electrons which are coming straight. Right. I think I told you in the beginning of this lecture. So if you put your detector here, you will get bright field image. Next comes this is number 2 detector. So this is used somewhere where you have, these are for Bragg diffracted electrons. So this is theta is Bragg angle. This theta is Bragg angle. Okay. And it's not easy actually that we will discuss this, because you can, this detector we can detect only at certain theta, right? Only one diffraction angle, but you have many diffraction angles. So how can it detect at other diffraction angle? So there is a trick, because you cannot make one detector for one angle, right, and another detector for another angle. So you just if I um, plot a cross section, so this is one diffraction angle theta 1. So another diffraction angle theta 2, right? So you cannot keep on making it. So how do you do that? How do you manage this engineering problem? Uh, I will tell you later on, not now. But I thought that someone of someone out of you will ask this question, that this detector is only kept at one angle theta, but how are you detecting other angles? Okay, so there you basically tilt the beam. Beam can be tilted actually. So there are some tricks. The beam is basically manipulated, not the detector, because detector manipulation is very difficult. You can't put so many detectors, but you can always tilt the beam easily, and that is done actually. So this is a beautiful, beautiful, beautiful image. This I have taken from the Barry Carter book, and this is so beautiful. You can keep on staring at it. You can spend half an hour on this. So, so this image shows you so many things actually. So you can see that it is an alloy of iron, chromium, and titanium. Okay, and this scale is the same. Yeah, this is bright field image. This one is bright field image, and this is actually color coded. This is EDAX image. This is simultaneously. So it is color coded by the atom. So wherever you see the red color, you see the iron atom, and you see the chromium uh, atom precipitates probably. Titanium is precipitating at one place. So that means you can see that this is a phase separation. You can see that there is something coming out of the main phase. It is not the same as the other area, right? Can you see this? This one, this particle, and you can see there is another particle. That means this chromium phase is separating. So uh, if you do not take this image, only most of the time students take this image. I was scolding one of my student uh, um, who works on dyes, that you're not doing the color mapping. So this is the disadvantage if you do not do that, because you will notice some changes here. But I told you that change in the contrast can be out of three things. I am repeating 10th time probably in this class itself. Crystallinity contrast, mass contrast, and mass means atomic mass or atomic number, or thickness. So here actually there is a lot of contrast. So how do you know that this is because of the mass variation, this contrast difference between this and this, or it is because of the different kinds of atoms are here, and here you have different kinds of atoms. So here, if you do this kind of analysis, you can clearly see that this is because of, not because of the thickness difference or something else, crystallinity, but it is some phase separation is happening. I mean, there is a different material. So chromium is precipitating here. So if you do not do this, you will miss out this information. You will not be able to know. And you can see that this is spectrum, and here these are the counts, and energy, and you can see nickel, aluminum, nickel, K alpha, 9 nickel, like these are your X-rays. So you know that X-rays have fixed energy following Mosley, right? Mosley's law. Again, we are bringing Mosley, and this is another beautiful image that you can just let me erase it. This image I love actually. You can see this is atomic percentage. So for example, when you draw a line like this, and okay, 20 nanometer, suppose this is your zero somewhere, 20 nanometer this side, 20 nanometer this side, and you can see 25 exactly. This is not exactly 25. This is around 22, I think. 20, 22 and a half. This one, 22 and a half here, 22 and a half here, because this 20 is here, right? So this will be um, So you can see that how the, I don't know where this scale was taken, but you can see that there is a variation between iron and titanium um, percentage. You can see this iron percentage is higher somewhere, and then and they are almost same. And one thing you would like to note, which the mistake which students they do, look at the error bar. Error bar is almost ±5. तो इन ईडेक्स प्लीज कान खोल के सुन लो, बाद में गलती मत करना। कान खोल के सुन लो, बाद में गलती मत करना, मुझे मत बोलना कि आपने बताया नहीं। ईडेक्स has got, when you calculate, please listen carefully, when you look at atomic percentage using edex, people always show me कि sir I have calculated iron percentage with the 10.78 percentage, and they're so confident, sir बिल्कुल बढ़िया झक्कास, एकदम मैं तो एक्सपर्ट बन गया, मुझे तो नोबेल प्राइज दे दीजिए, मैं इतना जबरदस्त कैलकुलेशन करके लाया हूँ। मैंने कहा भाई एक और डिजिट लगा देते यहाँ पे 10.78, तो तुम्हें 2 नोबेल प्राइज दे देते, एक और डिजिट लगा देते तो शायद 2-3 और मिल जाते नोबेल प्राइज। मैंने पूछा कि कौन सा इंस्ट्रूमेंट यूज किया है, did you go to Mars or some other planet, or did you had some secret collaboration with Elon Musk, to you are working on some special technique which you are not telling us, that you can so precisely calculate the atomic percentage using edex. नहीं, वो हमारा NCL वाला है ना, वो इतना बढ़िया देता है, ऑपरेटर बोलता है जो चाहिए वो मिल जाता है, इस पे इतनी डिजिट आपको चाहिए। और मेरा तो सॉफ्टवेयर इतना अच्छा है ना, ओरिजिन, उस पे 10 को डिवाइड करो 3 से, जहां तक आपको रुकना है रुक जाओ, 3.3 रुक जाओ 3। और मेरे ओरिजिन पे मैंने कर्सर यहाँ लगाया तो मेरे कर्सर में यही बोला था कि ये एटॉमिक परसेंटेज, आप ना, मेरे ओरिजिन ने ही मुझे बता दिया कि आपका ना कितना बढ़िया डेटा है, ऐसे ऐसे लिख दो आप रिपोर्ट, मेरे ओरिजिन ने बता दिया कर्सर पे। मैंने कहा बहुत बढ़िया। तो ऐसे तो साइंटिस्ट हैं हमारे, यंग साइंटिस्ट। सोचो अब ये लोग पागल है, ये लोग तो, इनमें बुद्धि नहीं है ना। यू कैन सी दैट you can see that they are not right, so they are okay. This is sarcasm actually. Okay, uh, you can see that they are putting 5% ±5 error bar. So our NCL students can produce 2-3 digits with so much of confidence, and see these guys don't have that much of confidence, that they are putting atomic number with ±5%। कॉन्फिडेंस की कमी हो गई इन लोगों में। इंडिया आ जाते तो इतना कॉन्फिडेंस दिला देते इनको, है ना। इंडियंस में हम में बहुत कॉन्फिडेंस होता है। Okay, so what is the spatial resolution? वो भी, I mean, our student can produce any resolution. You want whatever you want, they will give you, because their origin can give them any value actually. So yeah, so analysis of spectrum. I mean, there are spatial resolution has two answers. One is actually lateral, and another is vertical, depth wise. So sub-angstrom spatial resolution, this is basically lateral, okay? Because you see the data is collecting from the depth wise also, right? So sampling area, whatever I'm telling you. Spatial resolution is always lateral, but you are collecting the data from the depth also. Okay? I think we discussed last time, but I mean, it's not depth sensitive. I want to clarify it. But it collects the sample from, I mean, your data from the depth, sudden depth. So you have to be careful there. And EDAX is notorious there because you are using photons. So photons can look at the, basically, suppose what I'm trying to tell you is that whatever data you are getting, whatever this data is getting, so you do not ask that, suppose we take this particle, so how deep is the probe size here. I mean, for example, if I take a cross section of a particle, suppose this is a particle, we are looking from the side, okay, And suppose here you have a certain number of, let me do it in a nice way. So this is your particle you have made, and if I draw two lines, so suppose this is total is 8 nanometer or 6 nanometer, let's say 6 nanometer, and this is, let's say 2 nanometer, 2 nanometer, and 2 nanometer. Now, what is the guarantee that whatever values you are getting, all these values is the same here, here, here? This can be different. There can be a thickness gradient also, right? There can be a thickness gradient, right? So that is the problem, that this EDAX gives you, even if you can take nano probe, but this beam size is quite you can see that this beam size is quite deep actually for X-ray photons. So please be very careful. Okay, so you understand. So you are not making slices of this. You have reduced the resolution this way. I wish I were explaining. I mean, on the board in the class. Here it is very difficult for me to explain things, but I'm trying my best to explain these concepts in absence of the board. But I hope you understand what I'm trying to tell you. So all this data which you are seeing, this in this image, and that's why you can see. That's why you can see here in this image. You can see that you have the red dots here in the this side also, not just at the periphery, because if you see the rod is like this, right? I explain it in the class very well. So when basically when you are bombarding electrons, so they are going through this layer here and then this layer, right? When you're bombarding here, so they are going through this layer, Okay, here also they are crossing two layers actually in the middle also. So this is actually two layer. I would say two layer data, and this is actually a much more thicker data, because here at the periphery you have more path length for the electron. Just think about it. If you think, you will know what I mean actually. So all this data, especially for photons, when you are collecting photons, you have this problem of collecting data from. Yes, somebody was asking this question. So you can in an SEM machine. This is actually an SEM. This is not an TEM. Actually, you don't have much space um, in a TEM. So this is an SEM, and you can replace the detector. These are different probes. You can see this net kind of thing here. This is actually, I think, Faraday cage, and EDAX detector is already written. So this is the STM detector, and this is perhaps the sample holder. So sample holder looks like this. So you can put your grids here. Oops, you can put your 1, 2, no, not 1, 2, right? Some completely 2, 3, 4, 5, 6, 7, 8. I don't know what kind of nomenclature they are following, but you can see that you can put your grids here. So you can do it in transmission mode. So you can see another dimension. Okay, so here you can see, and you can see that this sits here, this guy. Okay, so this is how it is done. STM sensors attached with FESEM are much more sensitive. What is FESEM? I explained it. FESEM is the source is where electrons are generated by applying electric fields. You know, there are two ways, two main techniques. You need electrons, right? So you take some filament, either it is tungsten or lanthanum hexaboride, right? Those are the two materials with low work function and high melting point. So either you heat it and then electrons start coming out. That's old-fashioned way. These are called thermionic emission, right? Or you just if this is your electrode, you apply an electric field, and because of electric field, electrons are generated. So here you have much better control and much collimated beam, much brighter source, and much better. But this is much more expensive source than this one. So in regular SEM, you and regular TM, you get thermionic source. I will show you. It's in my drawer on planet. Next time I'll somewhere in the drawer. So FESCM is much better. We'll discuss in detail. There will be one lecture dedicated for that. Just so yields we have already discussed. When you do yields in STM mode, you get the same information, but from a very smaller area. So chemists will be very happy. They will be jumping with joy that you can identify the micro environment. I should not say micro, but you can see the beautiful image. Beautiful. So you can see that it's a multi-layer structure. And in fact, it's not a sample for chemist, but it's a sample from a physics laboratory. And scale bar, 1 nanometer. And what you see is rows of atoms. You can see those grid lines are actually the rows of atoms. Beautiful. Strontium titanate, lanthanum vanadate, strontium titanate again, lanthanum vanadate. And you can see yellow arrows point to the purple band showing vanadium titanium intermixing. You could not have seen this. So this tiny area here, where this there is a interlayer diffusion. There is always an atomic diffusion. So this is basically your. You can do it. You can find it out using ellipsometry. I'll be giving a skill development course using on ellipsometry next this month, end of this month. If you're interested, I sent you the information. You get the certificate. You can. So in using ellipsometry also you can look at interfacial mixing. So you can without of course there the problem is the same. Actually you have a huge there actually the problem is different here. There actually you have a lot of vertical resolution, which is the problem in sometimes actually not here, but sometimes it can be a problem in photon based electron microscopy technique. Okay, here you are detecting electrons, so its problem is not there because you're looking at, I told you the electron, there is no problem, resolution problem, but photon depth profiling will be at at a deeper level. So so that's why the problem which I was discussing earlier just now is solved here, because actually this is the depth profile, I believe. I'm not sure how the sample was mounted. I'm not sure whether it was lateral. I'm not sure really whether it was. I'm not sure how the experiment was done. I feel that it was like I'm not sure actually. I have to read this paper, but it does not look like the. No, it does not look like the vertical mounting. It's like lateral, I think. Yes, but anyway, you can see interfacial mixing here. I'm sorry, that cannot be done. sample is actually mounted like this. So it's getting scanned like this. Okay. Yeah. The TM has serious limitation because it cannot go layer by layer. It's not like you look at this layer first, then this layer. It cannot be done. So it's not like that because it will not be able to reach. Okay, so I was wrong. I'm sorry. You don't need to look at the paper. You can, by common sense, you can conclude here. If you have any question, please let me know. So this is another beautiful image. Graphite, again STM yields image. You can review this. And what you can note here is that you can look at nickel atoms, you can look at iron, carbon, okay, and this is STM Hadaf image. Yeah. Beautiful image, beautiful. If you publish these kind of images, if you are if you are working with catalyst or in organic chemistry, whatever, physics, so you can see how the impact of your research. I'm not talking about impact, general impact. This full image, another beautiful image. You can see that zoom this area, and wow, I mean, so much I can talk about this for hours actually. You can see this scale is 5 nanometer, which is very impressive, and if you see that there are 2 points, P1 and P2, okay, and this is corresponding peak for P1, P2. This is intensity. This is and this is line scan. Actually, it's called line scan. You see this line is drawn, the green line. So along the line scan, what you see is atomic percentage actually. Beautiful. So you can see that at P1, here the cobalt signal is all less, and then it increases, okay, and it peaks up at P1, and then it goes down, and then it peaks up, and then it goes down. Similarly for nickel also, it's like this, and this is done in yields. Why I'm emphasizing? You will have a problem in other techniques like Hadaf, because nickel and it is non-trivial, because nickel and cobalt, they are padosi, they are neighbors in the periodic table, right? They're exactly next to each other. Now the Z contrast is not possible because there is not much Z contrast. That is how much 27 for cobalt, and that is 28 for nickel. There is only difference of 1 electron and 1 proton. Okay, when I'm talking about charges, so incoming electrons will not be able to see any much difference. Same problem with X-rays. X-rays are even worse. You know the problem with uh, X-ray diffraction. It is not. That's why you use neutrons. Neutron diffraction is very useful because their atomic form factor is independent of atomic number. It just varies randomly, and that is the power. That is the beauty of neutron diffraction, neutron scattering. That's why people rush to the neutron facilities, because this problem cannot be resolved by anything. Please note that. Please note that it is very serious problem. What you see in the data. This can be done only yields. Yields can do that. Actually, yields has got high resolution actually. When it comes to the, I think I explained previously also. Yields can do that. So please appreciate the work of these scientists actually. It's very good. Beautiful example. I think you should read this paper. What is the energy? Yeah, we were just talking about energy resolution only. Here you have. So energy resolution can be beautiful actually. I mean, so suppose you have this typical energy, this range of beam, and then this is a spread delta E, which can be narrowed to if you are rich, and if you are rich, if you spend uh, 1 or 2 more crore rupees and you put a monochromator, then you can bring down the uh, energy dispersion in the source. You can make it more monochromatic, um, down to 100 MeV. It's a serious thing, it's a very serious number, believe me, for this kind of energies in kilo electron volt. We are talking about milli electron volt spread. So what it means that when you say 100 keV, uh, plus minus 100 MeV, it is mind-boggling. Actually, it's not easy. You need a serious amount of, because the problem is that electrons are coming from some source, whether it is a thermionic source or field emission source. Both do not. I mean, they don't have that less energy spread. Field emission is very good in coverage thermionic. Thermionic is बहुत बुरा होता है. If you are not sure what is the energy of your electrons, then how will you resolve these kind of signals? Okay, and and then again you put beautiful lenses, corrective multiple of lenses. Then it's a David Miller's Nature paper actually. It's another Nature material. It's again another beautiful article. You must read this. How he's a big guy. Structure and bonding at the atomic scale by STEM, David Miller. So you can see that spot size you have to reduce, right? I was talking about this beam size. It's not nanoprobe, it's basically sub nano. Amazing actually. You you see what it means? This is crazy. This is crazy. This is crazy. The beam size of this is the beam size. This is crazy. This is okay. It's acceptable. 3 angstrom. This is point half of angstrom actually. This is basically the radius of hydrogen atom, right? Half of angstrom. It's not a joke. Okay, so you can narrow down the beam to that level. So you need beautiful lenses actually. Magnetic lenses have to very good control. Your beam is not moving by even the diameter of hydrogen atom. It's not a joke. Okay, such a precise control. Then you can. So people, some students are very proby. They always ask me that, "No, what is the extreme? Oh, what is the extreme?" So I keep all these slides for those kind of students who always pushing me to tell them what is the best in the market, है ना? कौन सा सबसे बढ़िया है? मुझे वही खरीदना है. तो वो स्टूडेंट उस टाइप के भी होते हैं. अब जेब में पैसे हैं नहीं, उनको जानना जरूरी है. तो ये मशीन खरीदोगे, अब 30-40 करोड़ की आएगी. So to a first approximation, when a beam is, this is very serious business. Beam is placed on an atom thick column. Please note this line. It's very serious thing. Strong Rutherford scattering effect deflects the transmitted electron to form brighter feature in the annular dark field, with a less scattering between the columns. So you are looking at a column by column actually, one single column, atomic column, vertically. Inelastic scattering is strongly peaked in the forward direction, that we will see later on. So end of Hadaf STEM. If you have any question, then we'll go to the next serious thing actually, selected area electron diffraction, which is really which is used a lot at NCL. I mean, it's the most used technique. If you have any question, please ask me. Any question? No question.
Hello, sir.
Yes.
Sir, by ILS technique, means sir, stem ills or
What is
ills
your
are
name? What is your name?
differentiated. No, sir.
What is your
Sir,
name?
my name is Sir Priyanshi Pandey.
Okay, whenever you ask anybody, because I have not seen you, please understand that in the last season, you know, Big Boss last season, you know, we participants there was very offline classes. So students and I knew each other very well. You know, we used to uh, uh, we had a lot of interaction. So I could recognize the voice of the student, even if you put you know, if you blindfold me, मेरे आंख की पट्टी बांधोगे तो मैं मालूम कर लूंगा कि ये कौन सा स्टूडेंट है. But now I do not know who you are. So you are Priyanshi. So please, you know, introduce yourself. Anyway, continue with your question.
Yes, sir. Myself Priyanshi Pandey. Sir, my question is, sir, previously slide.
Are you from NCL or?
Yes, sir. I am from NCL, PMC
Okay.
division.
Okay. Yeah.
Yes, sir. Sir, by ILS technique, we also determine the allotropes of carbon. Means
Yes,
sorry, sir.
Priyanshi. Yes.
Yes, sir.
You're right.
Fluorine and C60 and
You're right.
graphene.
You're right.
But sir, not determine the diamond because pi interaction is absent.
No. Diamond, you can using yields you can easily distinguish. Diamond and graphite. Distinguish between diamond and graphite is very easy. Very easy.
But sir,
you can do it using just even with Raman. Raman is, see, the challenge there is sample amount. So in Raman, if you have a very small amount of sample, for example, you have this graphene quantum dot. Sometimes it's very difficult to get Raman scattering. Raman signal is so faint. Raman scattering is another problem. Cross section, Raman scattering cross section is very weak.
but
so,
sir,
bolo.
Yes, sir. But in the diamond, sir, no pi electrons present. So
Pi
how can
electron से
determine
मतलब
the?
नहीं है. Pi electron से कोई मतलब नहीं है. I mean, what EES looks at is the surrounding environment, difference in the surrounding environment.
Yes, sir.
It
Yes,
does
sir.
not mean, it has nothing to do with the pi electron or something else. It is very sensitive to the surrounding environment. पड़ोसी थोड़ा सा भी गड़बड़ हुए तो मालूम कर लेगा हमारे. ठीक है.
Yes, sir.
हमारी जांच पड़ताल नहीं. तुम कार्बन, कौन सा भी कार्बन हो, है ना,
Yes, sir.
कार्बन ही हो
Yes, sir.
एक्चुअली. पता है कि नहीं पता
Yes,
है?
sir. Yes, sir.
तुम कार्बन हो, पता है कि नहीं पता है? अधिकतर.
Yes, sir. I know. My
Don't,
organic. My
don't forget.
specialization is organic, sir.
Okay, don't forget. Sometimes we forget.
Yes,
We
sir.
think that I am Priyanka, but I forget that I am most part of my body is carbon.
Yes, sir. Carbon, hydrogen, oxygen. Yes.
So,
Nitrogen.
so any sort of surrounding environment. So that was an extreme example. You can see previous slide. There is an example that you can see the hyperfine splitting and other things. So
Yes, sir. Yes, sir.
yeah. Okay. So any other question?
No, sir. Thank you.
Somebody else? Somebody else? Okay. Selected area electron diffraction. So probably this will pick up in the, let's see how many slides are there. It is, let me explain it. Anyway, we are going to expand it in the next class. So forget about selected area. Then let us discuss about electron diffraction. If you follow these lines, so what you see is basically you me see if I have better. So let me draw my own curve. So this is so this is your sample. This is your sample. If you follow, there are one set of line which are coming straight. Okay, red lines. Okay, red, and they are. You can what you can put lens. This is lens, and once you put the lens, you can convert them to 1 point. They are undifracted or 0 diffracted. I change the color. Also, blue. Okay, blue. Now you see another set of curves, another lines which are diffracted by theta. Okay, हम theta यहाँ से बना देते हैं. ये theta है, ये theta है, ये theta है. अब इनको फॉलो करो. ये लाइन यहाँ से लेंस से फोकस किया, so it will focus here. I think you can clearly see blue line. Let me now select what yellow. So now you see another set of lines. This is yellow. This is yellow. This is yellow. It's another theta, 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 theta. Drag angle. So don't think that there are other lines which get diffracted at higher angles also. Those we get in hard arc. Okay, we have already discussed. So there are high angle पे भी electron scatter होते हैं. Okay, electron get scattered at higher angle, but they are not coherent electron. That's why you can just look at Z contrast. They don't have precisionity contrast. Okay, I think you know that. So if you convert these electrons, you can convert them here. This is exactly similar to your X-ray diffraction peak. So this is one peak. So if you see that this is same family of these are from the same family of planes, because the distance is same and this angle is also same, right? So this diffraction angle is the same. This from the same, these points are the same actually. If you okay, because it's a two-dimensional projection, so basically you can make a circle out of that. So there may be another angle theta 1, theta 2, for different. But what I mean to say that in the image plane, if you put a screen, then you will get something like this. Okay, this point is this point, and for example, this point is this point, and this point. Now, what about others? So these are actually corresponding point, and they are at the same in the same family. Okay, but because spacing is the same from the center, D1, D1, but now this is different actually, right? So now you can see that there may be other sets of diffraction angle, theta 2, theta 3, alag planes. So that's why you see different sets of. So this is electron diffraction, and it is you can analyze it, you can calculate the about your sample. You can do so many things. And you might be wondering that what are these tiny dots? You can see that there is another pattern between patterns, like a superlattice. So this is because of there is a precipitate phase. There is a phase within the phase. So this is an alloy, aluminum, lithium, copper. So probably you can see that there are some spots. What happens that one phase out of these three elements starts precipitating, and that is the reason that you see, and that shows its own Bragg diffraction, because that might be a crystalline phase. So that's why you see two phases. So you can reduce aberration and produce better diffraction pattern. So aberration is always a problem, spherical aberration and chromatic aberration. If you are rich, you can do that. Yeah. So these are some typical electron diffraction pattern. Okay, you can see how beautiful electron diffraction patterns are there. So you can get them. And this is कैमरे अपने मोबाइल को कल सेल्फी लेना है ना, धूप निकले तो सूरज की तरफ रख के है ना अपने आप को देखना, इस ये you get this kind of a streak, right? Pandey ji, Priyanshi Pandey, do you get this kind of streaks? एक तो
Yes, sir.
टाइप की आती है ना, क्यों आती है?
Yes, sir.
Why do you get that? कभी सोचा है कोई? somebody will tell me. Answer is written here. So because lot of, I mean, you are basically saturating the charge coupled device, CCD, you know, those sensors with lot of light. So that's why there is a blooming artifact. That's why the same thing, this is the same thing actually, because the sensor is based on the same science. Okay, so one should reduce the intensity. So this I included to show the artifacts. And nowadays there are better detectors. You can see that. You see another beautiful image. Okay, lanthanum carbonate crystal. Wow, very nice. You can see beautiful electron diffraction. And this is a comparison for you know, diffraction pattern from various kinds of samples. So if you have a mosaic of single crystals like arranged in a certain way, certain dimension, you get such a nice pattern, right? If it is plate, if you have a plate-like structure, which you many times you have, so you will see this kind of elongated lines. You see the dot has become like, you know, there is a elongation. You see the difference between this and this. So this, when you have a plate-like texture, if you have a polycrystallite, a jumbled up thing, then you get these uh, rings, concentric rings actually. But you can still use it. It's very useful. You can again calculate the diameter, and it will tell you the. Okay, so advantages will end in 2-3 minutes. Advantages of electron diffraction over X-ray diffraction. This topic will be taught in great detail later on, because many of the things you may not understand at this point. For example, what is a Wald sphere? I mean, so I think I can skip it right now. Okay. Yeah, this slide we can skip. We'll take it later on. So electron diffraction in TEM can be combined with direct mapping of the sample, and that including high resolution imaging of the crystal lattice and range of other techniques. For example, uh, you can you can solve and refine crystal structure by electron crystallography. Electron crystallography is a very powerful technique. I think you will appreciate now. You can do EDAX and you can do all kinds of things, but it has limitations also. I should focus on limitations also, that sample must be electron transparent. Okay. अब तुम्हें अपनी हड्डी पसलियां देखनी है तो डॉक्टर के पास जाते हो, है ना, और बोलते हो मेरा एक्सरे कर दो, और तुम्हारी मान लो हड्डियां इतनी मोटी हैं कि कुछ वहां से एक्सरे निकल के नहीं आ रहा, तो कुछ नहीं दिखेगा, सब काला काला हो जाएगा। डॉक्टर बोलेगा अरे क्या है ना, कैसे दिखाऊं तुम्हारे अंदर अंदर कैसे क्या है। या फिर तुमने कुछ मेटल की जैकेट पहन के आ गए हो तो यू नॉट बी एबल टू सी एनीथिंग, right? Suppose you have some transplant in your body, you won't be able to see anything, right? people go for this all kinds of tests to look at their lungs. So it has to, so you see the X-ray plate is on the other side of your body, right? So if X-rays do not penetrate through your body, how will you see the internal structure of your bones? The same thing is here. So if you are just interested in showing what is the size of your skeleton, okay, then outer circumference will be just dark something, you know. If you want to see just the size of your bone of your hand, that doctor will show you, no problem. But if you are interested in finer details, then it needs to be electron transparent or X-ray transparent partially. Same thing is here. Sample preparation is time consuming and it requires some special skills. And otherwise you will not see, you need to put, I mean, if you talk to some experienced student, they know exactly what concentration of some dispersant and how many drops and all kinds of things, how to dry, what to do, what not to do. So that is quite tricky. And believe me, colloidal sample, chemistry samples are much easier. Life of physicist and engineer is very difficult because sample preparation, they need to cut from a thick slab. That's why I got a little bit, you know, I spent time on that slide now. I was telling about this strontium titanate and lanthanum vanadate palladium multilayer structure. So because we are so biased with the chemistry sample that we do not, so they need to macrotome it actually, ultra macrotome. So they need to cut it in thin slices. Believe me, it is not easy to cut slices of less than 100 nanometer, and there are always a challenge of manipulating the sample. So life of hardcore physicists, sample preparation department is completely different actually. They are very serious people. They seriously they do their business. So feel yourself lucky that you are a chemist and you have colloidal samples which can be easily. Biologists, life, you know, life of biologists who are working electron microscopy is also not easy. They also need to do a lot of cryo microtomy. They need to freeze the sample and then cut them and then mount them. They need cryo TM holder, and it's quite tricky actually. For proteins, it's another challenge. And contrast problem is there. They need to stain it. So again, I'm giving you two extreme sides. Biologists, they spend a lot of time with sample preparation. Relatively, your life is much easier at NCL if you are a chemist. Okay, feel happy. Magnetic samples have a problem because of Lorentz force. Okay, I think we can end it here. Any question?
Hello, sir.
Yes.
Sir, myself, Hemant.
I'm not able to hear you clearly. Hemant, yes, Hemant, yes.
Sir, my question is, hello, sir.
Yes, I can hear you, Hemant.
Hello.
Yes, I can hear you.
Yeah.